Hi everyone.
Hi, ma'am. Good morning.
Good morning. How are you all? Joined document remaining girls into what is meant by I2C protocol. What is meant by yacht protocol? What are the applications of yacht protocol? Fast.
I2c is it's like a means multi-master, multi-slave kind of protocol. I2c.
Okay. Yacht.
Basically, like a synchronous and asynchronous concept. UART will be asynchronous. This I2C will be asynchronous. Means there will be a clock signal.
Okay. Fine. So yacht protocol is like it's a port where we communicate between system on chip, a processor to the outside devices. Okay, like any outside the device we can connect some microcontrollers or mobile phones or any printer or scanner devices, different types of external device we can connect, nothing but USB port. However, USB port is working the serial communication, same UART protocol also working. Okay, so outside the system, the communication between outside. Okay, but coming to the I2C protocol, it's a internal system communication. Okay, so integrated circuit, you already know the difference between intra and inter, right? Within the system and outside the system. Okay, so I2C protocol is internal system, we will connect one to one from microcontroller to the sensor or some ROM devices, like that we will connect internally. That's what we call as a inter-integrated, I2c also we call. That means double I. That means inter-integrated circuit. Okay. Today we are going to discuss the detail about the I2C protocol, the working functionality, and what are the major features of I2C protocol, and what are the different versions of protocol, and uh, two major concepts we are going to discuss in I2C protocol today, and also how to write the Verilog HDL program, the design code. Today I will explain you the how to design using finite state machine. Tomorrow session we will discuss on how to write the RTL program and also system Verilog verification. Okay, and also we will discuss the major features of I2C and I3C. We have I3C protocol also, which is an advanced protocol compared to the I2C. Tomorrow we will discuss those differences, and also we will just discuss on SPI protocol, because SPI is also more advanced protocol compared to I2C, and also it works at a high speed. So we will see the differences between these tomorrow. As of now, today's session we will discuss the specification and what are the best features and what are the main concepts you need to learn for interview purpose, and how to write the programming like finite state machine. How can we create a finite state machine for I2C frame format? Okay, so whatever the doubts you have, please ask your doubts. So we will start with the I2C. First of all, I2C is a multi-master, multi-slave. What is meant by master and slave? Master is nothing but the initiator. Suppose transmitter side, whatever the block we have, we call it as a master. Master is nothing but a initiator. Slave is nothing but it will get the data from the master. Whatever the master initiated some transfer, the slave will receive that data and it will respond to the master. That's what we call as a master and slave, transmitter and receiver. Okay, if you see your protocol, we have only single master, single slave. That means protocol side we have one master. Suppose your laptop is there, you can connect one protocol, I mean one port to another port only, single port only. Okay, suppose we have multiple ports in the laptop. I'm not talking about the multiple ports. Suppose one port to one mobile phone, or same port to some any music system, or any scanner or printer, or even mouse, or keypad, external keyboard. Okay, so like that you can connect one to one, only one master, one slave, or only one transmitter, one receiver. But coming to the I2C protocol, we have multiple master, multiple slave. Okay, like there are three different microcontrollers are connected to number of slaves. Okay, like that we have the multiple number of slaves. We will discuss that. We'll see the clear picture so that you will understand. And also packet switched. Packet switched in the sense what we will send the data in terms of packets, nothing but in terms of bits. One packet have n number of bits, right? So like that, one by one bit will be sent serially. So 0, 1, 2, 3, like the same as a UART protocol. One by one bit will be transmitted from master to slave. And single-ended. Single-ended in the sense one to one. And finally, we will have one output, right? One slave connection. And also it's a serial communication bus invented by Philips, now NXP Semiconductors. It is used to connect low-speed peripherals to processors and microcontrollers in embedded systems. Okay, and coming to the I2C versions, we have lot of versions in I2C protocol, but commonly used, what is the common version in the sense of V1.0? It's a original specification. In original specification, we will have overall I2C idea. That means master, slave, how the masters and slaves are connected each other, and how the signals are connected, the frame format, SDA and SCL signals are connected each other. So that is original specification. But coming to the versions later on, whatever V2, V3, V4, V6 are there. So these versions are nothing but fast mode, high speed mode, ultra fast mode, like that. Okay. So V2.1 comes under fast mode 400 kbps. Before it's a 200 kbps means extra bits per seconds are increased. The speed of the I2C protocol is increased. Okay, and coming to the V3, it's a more high speed mode, up to 3.4 mbps, from kbps to mbps, like that. Fourth version, ultra fast mode, mbps and unidirectional, like that. Fast mode plus 1 mbps up to 1.8 volt it will support. And 7 new features like in-band interrupt. Mostly this feature is available in I3C protocol also. We will discuss some basic topics of I3C protocol tomorrow. And also the target reset clock stretching concept is one of the best important concept in I2C. And also interview point of view, mostly you will be getting clock stretching concept, and how the master slaves, I mean multiple masters are connected to the slaves using arbitration concept. These two are very important. And in I2C, we have a clock. If you see in your protocol, we don't have the clock, right? How the synchronization happen between master and slave? Through the baud rate. We need to consider the master side baud rate and slave side baud rate need to be equal. Both baud rates should be maintained at the same clock frequency, and then we are communicating each other. But in I2C protocol, we don't have any baud rate. Directly, we will communicate through the clock, master side and slave side. Okay. Clear till here? Any doubts?
What do you mean by low speed peripherals? Like what
Low
device?
speed peripherals means we already discussed, right? The small sensors or keyboards, or mouse pointer,
Okay.
or these small EP, not ROM, those work at a high speed. Like UART, SPI, these things will comes under low speed peripherals. In system, I think, are you not there in first session?
No.
Okay. So I will share you the recorded session. From that you will understand. In system on chip design, we will have high speed blocks and also low speed blocks. So high speed in the sense it comes under processor, memory systems, or direct memory access controllers, graphic processor. All these things comes under high speed. Coming to the low speed peripherals like sensors or Bluetooth, Wi-Fi module, GSM module, or keyboard, mouse pointer, these things, keyboard, mouse pointer, all these are perfectly suited for UART and I2C because we are connecting outside the device. Internal device, Wi-Fi, GSM module, these comes under low speed peripherals. Okay, so like that we need to divide. I will share you the recorded session of that. You will get understand.
Okay.
Hello.
Yes.
So what exactly meant by that single-ended?
Yeah, we will discuss that. So coming to here, so if you see a bus architecture of I2C protocol, it have two wide signals actually, SDA and SCL. SCL in the sense serial clock, SDA means serial data. Okay, and it having open drain lines with a pull-up resistors. What is meant by open drain pull-up resistors?
It's a
Mean
kind of a normal wear kind of thing.
Okay, so how these are going to work? Okay, we will discuss. Another thing, please mute everyone. If you see here, multi-master support and serial data transfer in 8-bit chunks. Mostly I2C protocol supports 8-bit data to 10 bits data. Okay, so here I2C bus, the data here maybe some other devices are connected, some master, and data is connecting to the I2C bus. Maybe this data coming parallelly, but I2C is a serial communication, so parallel data will be converted to the serial data to pass different devices. So SDA is a serial data and SCA is a common clock to all. So if you see here SDA, how the all devices are connected common to the clock and data. So same data is distributed to number of uh, blocks, chips. So here there is a microcontroller and some IC chip and some another type of sensor device and another type of FPGA or any microcontrollers. Like this, it will be connecting. And coming to the two resistors here we use in I2C protocol, we use open drain I2C. Open drain in the sense both SDA and SCL clocks are designed as an open drain or open collector. Okay, so we have the for transistor, we have collector and gate and drain, right? So here we will use that concept. If you don't understand the uh, transistor concept, just check that and you can understand this. Okay, so here devices, whatever the devices are there, they can pull the line low. Okay, that means it will be 0 volts or logic 0, but they cannot drive it to high, whether 5 volts or logic 1, because instead of a pull-up resistor, it is used to bring the line high. So no device will pull it to high, or it can do low. Okay, so why we are using the open drain in the sense here? It will allow the multiple devices to share the same bus here. If you see the device 1, 2, 3, 4, 5, all are sharing the same bus here. Okay, so without any conflicts or without any short circuits, we use the open drain concept here. So if one device pull SDA low, SDA signal low, another one try to pull it high. So using a push-pull driver will be there. Push-pull driver concept will be there. That all comes under implementation part. But as a design and verification engineer, we need to transfer the data properly. Okay, implementation wise is different, and how the frame format is transferring exactly, that will be different. So our work is to design the frame format exactly and pass the data and address to the master and slave. Okay, so here short circuit risk will be happen whenever one device is pulling SDA low and another one trying to pull it high. So short circuit effect will be happened. So whenever open drain plus pull up resistor device only pull low and high is managed by the resistor, this resistor. Okay, so that is what the here in this case we have the smooth communication, or else it will be short circuit effect whenever SDA is low and also it is trying to pull up high, then we'll get the short circuit effect. That's why we cannot drive it too high. We can pull the line to low only. I mean, devices can pull the line to low only. Okay. So here pull up resistors are connected between mostly 3.3 volts to 5 volts. From 3.3 to 5 volts. So when no device is pulling the line low, the resistor will bring to the line high. So whenever any device pull low, the line will go to logic low. So that is what the pull-up resistor, just for the communication, how the devices are sharing the bus, it will be dependent. Why it is important in the sense bus sharing? Because all are sharing multiple masters and multiple slaves are there here, right? So for safe communication, to use the same bus safely, we use open drain plus pull-up resistors for safe communication between all the devices. Okay, for common bus. And also it supports the arbitration concept. Arbitration concept means what? Suppose there are multiple masters. Here there are 3 number of masters. All masters are trying to initiate the transfer at a time, but only one master need to connect to the slave, right? So which master will be that? Which master can run the bus first? Which master can send the data first? We need to write the arbitration concept here. Okay, you will get the clarity by end of the session. So arbitration support will be there, and also low power, because of these two devices are controlled by this line. It pulls low, so low power uh, power consumption will be happen. Okay, so this is how the structure of I2C protocol basically. If you want to calculate the pull-up resistor, like if you want to calculate what is the rise time, what is the pull-up resistor, and the capacitance, you can also calculate like rise time. So rise time will be the 0.8473, but for you it's not required. Just I am telling, into RP. RP in the sense pull-up resistor. So what we need to find? Pull-up resistor into CB. CB in the sense total bus capacitance. Okay. So you can calculate like this and you will be getting the rise time. Rise time, why it is used? It just define the I2C mode. Suppose here we have different types, like fast mode, high speed mode, ultra fast mode, fast mode plus. How all these modes are defined based on this rise time and pull up resistor and the capacitance. The whenever we are increasing the value, the rise time value, the mode will be increased. So less than 1000 means what? It's a fast mode. Okay, like that. Greater than 1000, it will be ultra fast mode. So based on these signals, we can increase the uh, data number of bits per seconds. Okay, understood
Ma'am,
the
please
concept?
write the formula again.
TR is equal to, I will tell you right now. TR in the sense rise time. Rise time is equal to 0.843. 0.843 is the fixed value. What is meant by 0.843?
Fixed value.
Time required to send the data, sir.
Time required to send the data. Okay. So actually it's a it comes RC, resistor capacitance circuit analysis will be there, right? So for RC circuit, we use this voltage rise up to 30% to 70% of VCC. So that's why rise time will get RC into 0.8473. That's why we need to use 0.8473. Just it's a scaling constant value. Okay, so that's why TR is equal to 0.8473 into R into C. R means pull-up resistor, C means capacitance, total capacitance. If you are interested, can calculate or else not required. Okay, but better if you have understanding whenever the question rise in interview, at least you can remember the concept and you can tell. Because of pull-up resistors here, how the fast, like in I2c protocol, we are using different modes like fast mode, ultra fast mode, like that. So how it will be calculated means through the resistors. Whenever we are increasing the speed of the scaling of the resistors, the rise time, automatically the mode of speed will be increased. Okay, so this is what the I2c concept. In your protocol, we have frame format, right? What is mean by frame format? Nothing but how the data is transferred. If you observe, I already told you, we don't have the address. Why don't we have the address in your protocol? Can you tell me?
It's a single master, single slave.
Single master, single slave. Okay. Because of single master, single slave, we don't have the address. Huh?
No, for if you have a single slave, there will be a particular slave is addressed by the only one location destination is there, correct? Then we have start and stop bit means we can do the synchronization, correct? There won't be any the data won't be going to somewhere else or some other address, correct? Because it is destined for only one particular slave.
Okay, fine. Any other answers? Others? I already told you. For UART or USB protocol, we will have one-on-one communication. So one-to-one, it just directly transfer the data in a serial communication. So no need to select the address here. Anyway, it's a one-on-one communication, right? You just transfer the data. No need to select the address. Address means what? If there are multiple number of slaves, 4 number of slaves, every slave have particular address. So at transmitter side only, it will select the address and will send the data to the particular slave. Okay, but here we don't have the address.
Ma'am, hello.
Yeah.
Can you go back to the previous? I have one doubt over there.
Okay.
Here, if I have the SoC or the CPU or microcontroller, which will be the master? Okay. In that case, I in the SoC outside, I mean boundary of the SoC, I have will be the IO pad, means IO pad or I2C dedicated pins. So the CPU want to access some temperature sensor or pressure sensor or something. It will come to these particular pins and it will take the data from the sensor. That is what is the bus you are showing in the dark color, correct? Okay, so so the arbitration will be done before the green box, correct?
The arbitration, yes, whenever we are initiating the transfer from master, then only arbitration will be done.
Okay. So if I only have 2 pins. I have multiple sensors are outside the sock. So how I will know which one need to select, which one need not to select?
Which master need to select?
Master will be CPU. Master will be CPU because it is inside the sock. Correct? Microcontroller or CPU, those resides inside the sock only. Correct.
Okay.
I want to access the data from a sensor. Okay. One slave sensor I need to access. So how, because then there will be multiple, consider if I have multiple sensors outside the SOC. From each
Hmm.
sensor I have to
That's why we are
take the,
using the address concept, right? To the particular address. Particular address is nothing but slaves. If there are 4 number of sensors, which sensor you need to pass the data, internal system need to understand. So there we will select the particular sensor address.
but you mentioned a master means also masters outside that green box. That's what confusing me. Normally in the if you have a boundary, one left side will be the masters, right side will be the slaves, means
Hmm.
all the slaves are outside. I thought like that, whether it is
No,
correct.
no, no. Here, internal SOC, it is not communicating outside the device. It is not a port. Internal SOC also we will have the sensors, right? So internal circuit, it will be communicating, not outside.
Okay.
Internal SOC. So if you see the block diagram here, I kept. See, internal SOC only. We will have these many circuits. Like there will be one microcontroller and second microcontroller, second master, and there is a gyrometer and OLED display and EPROM and some temperature sensor. All these circuit is one. Maybe it's not related to laptop, but any electronic device. Within a electronic device, we have these many controllers and also OLED display, some temperature sensor, and some gyrometer, like that. Okay, so in this case, how the I2C protocol is communicating each other. Suppose there is a washing machine. Washing machine is nothing but we have a microcontroller, and it also having this display, and it will be having some temporary memory, and also it is having some sensors, right? For water sensing. For level, it will control the level, sensors will be there, so everything, this whole circuit will be there in the washing machine. So in that case, how it is communicating each other, like that.
Okay. Means
Outside the
it will
device, not
it.
external device. Yeah,
Okay.
yeah.
So arbitration means which master on which particular side, like that it will do. Correct. Means
Yes,
it
suppose here
prioritize.
two microcontrollers are there. uh, these two are working same. Suppose same washing machine, if you take for washing cloths, we connected to one microcontroller. For drying the cloths, we connected to one microcontroller. There are two microcontrollers. So washing and dry both cannot be done at a time, right? First we
Hmm.
need to connect the washing side to the microcontroller. Once the task is completed, microcontroller will do only specific task, not all task. Like a processor will do every task, whatever the instruction we are running regarding the arithmetic and logical operations, every task it will be done by processor normal. But microcontroller means only specific task. If this microcontroller is designed to wash the clothes, if we dump the program to wash the clothes, it do only washing. It is only for drying the clothes. Okay, so once the master is completed its task washing, then dry task will be on. That means washing machine will go to dry state. Okay, so that thing will be controlled by these microcontrollers. So which one should work first means, obviously it both have the priority. Priority one is washing the cloth, priority two is drying the cloth. So like that we will give the priority using arbitration concept in I2C protocol.
Okay. But overall, these masters will be controlled by the processor with respect to the
Actual
interrupt.
processor will be there. Yes.
Okay. Yeah, thank you, ma'am.
Yeah. So when we say arbitration, it chooses which slave, or even for master also is there arbitration?
Only master, not for slaves. Only master. Once
Okay,
we
so
see simple concept, there are two masters. There are two number of operations, washing, drying. So which you need to do first? Washing. Washing means first arbitration will be selected master 1. Master 1 will run the bus. Will run the bus means through this washing, all the sensors, whatever the washing task is there, all the sensors will be activated. It do its a task. So washing is completed. Now dry. Dry in the sense this bus will stop connecting with the sensors, and the dry, whatever the microcontroller is there, that will give the data to the bus. That bus will be one that transfer the data. So whatever the sensors or remaining circuit is there connected with the dry microcontroller, those will doing the operation. Okay, so based on priority, here we have pull up and pull down resistors, right? So by using this also we will write the priority. Totally how we are writing the program, I will explain you how to write the program for arbitration concept and clock stretching concept. Okay, simple concept. Microcontrollers need to select arbitration side. Slaves will be selected microcontroller side. That means masters will select the slave through the address. There is a slave 1, slave 2, slave 3, slave 4. So the master will select the particular slave using the address, and it will be sending the data to the particular slaves. Okay.
yeah.
So I think everyone got the clarity of I2C and how the data is transferring. The frame format. Frame format is very important. In UART protocol, we have seen the frame format, right? Stop condition and first start condition, sending the data, and we are checking the parity signal, whether the data is correct or wrong, and then stop signal. Same in I2C also same concept, but little modifications. So if you see here, there are two signals, SDA, SCL. Okay, so SDA is a serial data, SCL is a serial clock connected to all the masters, all the slave commonly. Okay, whenever SDA is high to low, and SCL is constantly high, it called start condition. Okay, whenever SDA is high to low, SCL is constantly high, we call as a start condition. Here address A6 to A0, 7-bit address, totally 8-bit actually. In that 8-bit, 7-bit will represent address, last bit will represent write or read operation, whether it's a write operation or read operation. Okay, and acknowledgement signal. ACK in the sense is an acknowledgement that will be sent by the slave, whether it is received a proper address or not. Acknowledgement signal or not acknowledgement. If it is received properly, it will be sending acknowledgement. If it is not received properly, it will be sending not acknowledgement signal. Okay, and coming to the data, so address is okay, address is passing to the slave. Suppose what address is it? It is passing 0 1 0, suppose 7-bit. 2 means second slave will be connected to that particular slave. We need to send this data D7 to D0, 8-bit data we need to send. Okay, so after passing 8-bit data, we will get the acknowledgement signal again. Why? Because we need to check whether the data is correct or wrong. If data is correct, acknowledgement will be high. If data is wrong, not acknowledgement signal will be high. Both the ACK and NACK both one signal only. If high, ACK will be activated. If zero, and NACK not acknowledgement. That means we have some error or data is incorrect or address is incorrect. Okay. So here we pass the data, 8-bit data. I2c protocol have the what is the maximum data in the sense 8-bit to 10-bit. We can transfer based on the versions, 8-bit to 10-bit. And coming to the stop condition, we need to know in which case we need to stop the transfer, right? So what is the stop condition? SDA must be low to high. SCL must be constantly high. In this case, it will be stop condition. SDA must be low to high and SCL must be constantly high. It will be the stop condition. Okay. So this is what the frame format of I2C protocol. By using this frame format, we need to design the finite state mission. By using the finite state mission, we need to write the design program of I2C protocol. Okay, this is what actual concept. Did you understood here?
Hello.
Yeah, tell.
So basically, we will have 8 cycles, 8 plus 2, 10 cycles to send the address, then 9 cycles to send the data.
Yes.
That's how.
This total address we will send directly. Acknowledgement is a response. We don't send. We will get the data from slave. We will send total 8-bit address to the slave. In that 8-bit address, first 7-bit will be the address. Last 1 bit will be decided by either read or write.
Okay.
Okay. And 8-bit data. So how you will write the final state mission for this? How do you write final state mission?
First, we can start checking the start condition.
Okay.
And then address. Like we capture the 8-bit address and then we see if it's a read or write operation.
Okay.
So if it's a write operation, we will write the data into the slave. If it's a read operation, we will try to get the data from the slave.
Finally,
Fine.
ma'am, when we stop the process.
How we will write this SDA and SCL in a final state mission? Like how we write the expression?
Ma'am, 0 ideal.
0 0 ideal. Okay.
Ma'am, when we have to start, we will put SDS 0, SCL1 means 0 1.
Okay.
When start condition occur, when we will pass the address.
Okay.
After that, ma'am, I am able to think.
So we'll check that last first bit, depending whether it is read or write. So depending upon that one, if it is a read bit, means we will enable the receiver, and means we will take the data from the slave end.
Okay, fine. It's not as simple like that. We need to write a lot of conditions. We will check. We will see that thing. So next, coming to the theory, just whatever I explained till now, same. It have the master and slave. Master is nothing but initiate the data transfer and control the clock. Slave is nothing but it responds to the master request. And each slave have the unique 7-bit to 10-bit address, and addressing will be 7-bit address is a standard mode. Up to 128 devices you can connect. 10-bit address means up to 2 power 9 number of slaves you can connect per more number of devices. And read or write operation I just discussed, right? Address value 0 means for write, 1 means for read. Last 1 bit will be decided whether read or write. And acknowledgement signal or not acknowledgement signal. The receiver will pull the SDA low during the 9th clock of ACK. Okay, so that we will get the response from the slave whether the data is correct or wrong. Next, acknowledgement. Again here, if you observe, it is a 9th bit of the frame. This is the case for all frames. Once the first 8 bits of the frame are sent, the receiving device is given control over SDA. And if the receiving device does not pull the SDA line low, before 9th clock pulse, it can be inferred that the receiving data either did not receive the data or did not know how to parse the message. Okay, so whenever it is not low, maybe it is not received the data or it did not get any how to send the message. In that case, the exchange halts and it's up to the masters of the system to decide how to proceed. Normally, the slave need to send the acknowledgement signal. Obviously, it will send the acknowledgement signal. If it is not receiving somewhat connection problem or it is not able to send the data. But if it is send the data based on the 1 means acknowledgement correct data, 0 means not acknowledgement. Maybe in which case we will get the not acknowledgement. What are the chances of getting not acknowledgement signal? Can you tell me? Suppose here one master is there and 4 number of slaves are there. So the master is initiating the transfer to 4th slave. Address is 4, but the slave is sent as a not acknowledgement. So in which case the slave can send the not acknowledgement?
Slave may be busy with some other master.
Okay. Slave is busy with some other master. If it is other master, slave is busy, other master means, then this master cannot able to send the data to slave, right? One time only one master is active.
Okay. Frame error. Some
Address might be a issue, like address decoding issue.
Okay. Address decoding issue, then it cannot send to the particular slave. Okay. Maybe address issues or even slave is busy with some other signal, not with the master. Maybe before any transaction, before master is completed its own transaction, but slave is still it is working with its transaction. Here the bus will cut and master will get second transfer. So slave is still busy in this transfer. Okay, so that time also we will get the not acknowledgement as just to wait for some time. The slave will respond like just to wait for some time. So that is what called not acknowledgement. Okay, if address is not matched also, we will get the not acknowledgement. If any slave is busy with that particular address also, we will get the not acknowledgement signal. Okay, clear?
yes.
Next, what are the advanced features of I2C protocol 7.0? Nowadays, we are using 7.0 in I2C protocol. So, what are the major differences? First, fast mode. Fast mode in the sense the speed is up to 1 megahertz. It higher drive strength and noise margins. So what is meant by noise margin here?
Is
No
it like
idea?
is it like we are sending the bit by bit wise? So any interference or external interference comes, right? The data the probability of data getting corrupted is high. Is that
Okay. Nothing but we will have the signals, right? Logic high and logic low. Nothing. Noise margin is nothing but external noise will get interpreting in the logic signals from low to high. So minimal change will be there between voltage high and voltage low. That's what we call as a noise margin. Suppose voltage high is actually 3.5 and low is 0.5 like that or 1.5. We will calculate the noise margin between high voltage to low voltage. Suppose actual voltage is 3.5, but due to the noise it went to 3.0 and here it may went to 1.5. So due to the noise, external noise, we will get the values in this way, like fluctuated values. Okay. So we will calculate the noise margin, high voltage minimum value minus low voltage minimum, or else low voltage maximum value minus low voltage, high voltage maximum value minus low voltage maximum value. Like that also we can calculate. That's what we call noise margin. So next, high speed mode, fast mode, after fast mode, high speed mode, and then ultra high speed mode. Clock stretching concept, we will discuss about the clock stretching. Next, coming to the IBN, in band interrupt. It is in I3C concept actually. Tomorrow we will discuss the I3C. And coming to the packet error checking, so whatever we are sending the packet 8-bit size data, we will check the data is there or not. The CRC based error detection, CRC checks will be there, right? So cyclic redundancy checks. So based on that concept, we can detect the error, and especially used in SM bus, in the sense system management bus. In the first day, for you, some of students, I have shown you actual SOC design in how we use, right? In that there will be system management network for every IP. In every IP, we will connect SMN. Okay, so that SMN is used to check whether the errors are getting or not. It will detect the error in system management. So that is introduced in 7.0 version. In first basic version we don't have that concept. Okay, and next thing is a multi-master arbitration. Multi-master in the sense the same we discussed before, but we need to write the arbitration concept to select any one of the master to run the bus. So we will discuss that multi-master clearly. And repeated
hello?
start condition. Yeah, tell.
In the previous slide there is a CRC. Is it similar to that UART parity check?
Your parity is different. That is just parity checker. Here CRC means a cyclic redundancy checker. That concept is different. CRC concept.
Oh, okay.
CRC concept is different. Here we will write cyclic redundancy check. That means we will have the frame format same, but it will be checking through checksum. Checksum means what? The code will be there. CRC code will be there. Through that code, we need to generate the checksum at sender side. So whatever the received data is there, it will be received the correct data or not. That thing will be checking. Actually, basic I2c protocol doesn't have the CRC by default. It only support the acknowledgement and not acknowledgement system by using the simple one bit, whatever we have discussed before. But later on in new versions, so these SM bus, PM bus, I3C, like that introduced that CRC data transmission will be happen. Nothing but suppose data.
So is it like the cross-checking whatever data we sent at the receiver side, it is the expected data itself. That's what it is checking.
Expected data, not expected data. Suppose here we are sending the data like this. We need to use the polynomial CRC polynomial concept. You can even search. We need to use the polynomial concept. What is the expression for polynomial? X cube plus x plus 1. This will be the polynomial expression for the CRC check. So from this, if you calculate, you will get the binary data. So for that, you need to append the zeros from binary data, whatever the CRC size is there. You will get the actual data, CRC code. That's what we detect the error. If the remainder is 0, the data will be valid. If remainder is not equal to 0, error will be detected.
Okay.
Just check
Thanks,
the
ma'am.
concept, you will understand. Okay, next multi-master, multi-slave concept. We will discuss that. Next, repeated start condition. Repeated start condition means same before till acknowledgement is completed and next transfer is initiated. Till then, we cannot do the repeated start or stop conditions. But here we can do that. It allows the communication with multiple registers of a device in a single session and prevents other masters from taking over the bus. Hot swapping. Hot swapping is nothing but same I2C devices can join or leave the bus without affecting ongoing communication. Suppose two microcontrollers are there, two masters. If any microcontroller don't want to transfer the data, it just want to leave the bus, then it will drop without affecting the present communication. It will just drop from the bus. Okay, so that concept is called hot swapping here. Next, low power support. Anyway, whenever the features are increasing due to the clock stretching concept, and it will use the sleep commands. Sometimes even most of the microcontrollers will go to sleep mode, right? The sleep mode is possible. So those concepts are introduced in 7.0 and 1.8 volts IO support in FM fast mode plus and later versions. Ideal mode when no communication is active. So it supports the low power communication and also error handling features in the sense same acknowledgement, not acknowledgement. Whenever arbitration lost, it will detect that. That means arbitration lost means 3 microcontrollers are there. Only one microcontroller can run the bus and it can able to send the data through the bus, right? Suppose here 2 microcontrollers are there. Only one microcontroller can work at a time. Other microcontroller will lose the bus. So it will detect which controller has lost the bus also. And it will check the clock stretching, timeout, and PEC for error checking. Next, I2C master support multiple master So I just explained, right, how it will be working, microcontroller 1 and 2, and remaining slaves, how it is connecting. Next, coming to the arbitration concept. Arbitration concept, clock stretching concept, we will discuss. Before that, we will write the program, we will write the finite state machine for this frame format. Can you explain how to write the FSM for this?
Sir, please explain SDA and SCL once more.
SDA means serial data. Through the SDA signal only, we are sending address and data. SCL means clock. Okay. In your protocol, we have start condition and stop condition. Whenever start is high, we have initiated the transfer, data transfer. So we can able to transfer the 8-bit data. Whenever stop is 0 or stop is high, we can able to stop the data without transferring. So that is what start and stop condition in UART protocol. Directly we kept 0 and 1 in UART, because in that we don't have the clock signal, we just have the baud rate. So directly we put the values. But in I2C protocol, we have SDA and SCL. That's why for these two, we are writing a common expression or common logic. What is that? SDA must be high to low. Whenever SDA is high to low and SCL is constantly high, then it is start condition. Okay. Whenever SDA is low to high and SCL is constantly high, then it is a stop condition. Start a stop. In between, address a data transfer. Okay.
Yes, ma'am.
Now, how to write the finite state machine?
First, we can consider an ideal state like where both SCL is 0 and SDA is 0.
Okay. Wait, let me write the product. Let me write. Tell. First of all, master and slave, which one will initiate the transfer?
The master.
Then what about the slave?
All
The
slaves
slave.
will be getting the address. So whenever the slave address matches with a particular address that master sends, they will be start communicating.
Okay. So
Slave give acknowledgement
master
signal.
will be initiating master is nothing but initiator. Slave is nothing but it will respond to the master, right?
Yes.
So can we take like master is a test bench and slave is a design?
Yes.
Yeah, same like AXI. In AXI also for design we do slave and test bench is the master.
So master side we can we can initiate the data and slave will be design. So anyway, master side we write the test bench, we write the system verilog verification test bench for so how can we design a slave FSM? Slave FSM. What is the first state?
to detect the start condition?
First state will be the ideal. So what will be there in ideal state? First of all,
Both
how many
STL
states
and
will
STA will be 0.
ideal state? First of all, let me tell how many states will be there. Ideal is start. Next,
Wait.
start,
Address,
address, register address. Next, acknowledgement, register acknowledgement. Next,
Data transfer.
read or write. Yeah.
write data. Next,
Read data.
what about acknowledgement?
Not acknowledgement will be there, right?
Only
Right, data
acknowledgement.
acknowledgement.
If acknowledgement signal is 1, it will be acknowledgement or else not acknowledgement. By using single bit only, we will decide. Okay, next.
Read data, acknowledge.
Read data. Read data acknowledgement. Okay, next.
Stop.
Hmm?
Stop, the stop condition.
Stop. Okay,
Initiating new transfer.
Waiting for wait.
stop, wait. Stop state. And then for new transfer, go for start state. Okay, so first what we write in the ideal?
Both the lines will be 0. SCL and STA.
SCL and SDA both will be 0, na?
Both will be 1.
No. What's your name?
Ashwini.
Okay. First of all, in ideal state, it will go to the start state, right?
Data will be there. Clock will be there. Data will be 0.
SDA once check again. SDA is low to high. Sorry, high to low. SCL is constantly high. That means SDA will be edge trigger. High to low. And SCL must be high constantly. Now slave will go to start condition. So
Ma'am,
here,
hello.
yeah, tell.
So basically, if I have a master and slave, means if I have a clock port, means both will be connected or shorted, correct? Then how can I make a high for a particular scenario? It will be toggling, correct? If I have a clock coming from the master and that clock port will be connected to the slave, it will be always toggling, correct?
Okay.
So means how I can say it is high? It is just like a clock. Its clock signal will be connected, right? It will be synchronized with between the master and slave. Like that only we can say, correct? Or
Here, what can you tell again?
if I have a master and I have connected to different slaves, all slaves should get the clock, correct?
Okay.
The clock signal will be shorted, correct? Or it will be coming from somewhere the clock won't be high always, right? It will be toggling. Or will I be using some gate controlling technique to stop the clock? How it will be?
Yeah, clock is always like this changing.
Okay.
So at the same time, whenever the clock is high constantly, SDA must be high to low. So when both are matched here, we can initiate the transfer. Whenever constantly clock is high and SDA must be low to high, in this case we can stop. We will write the program according to that.
Okay.
Those are start and stop. In the middle, it can be either address transfer or data transfer. And if you see here, clock is constantly low, and here it is SDA is high to low, not transferring any data, and clock is also low. And remaining all cases, normal clock is working normally, and SDA also sending data. Okay.
So how that clock is low in between means we are stopping the means we are controlling the clock in between, like that it is happened. That's why that.
What here we call as a clock stretching concept, because here SDA address is there, and passing the data to the slave, and slave is still keep on working with that present operation. Then in that case, clock need to wait until it complete its transaction. Once a slave is completed, once acknowledgement signal is generated, then the clock will be go to high, and the data transfer will be happen next to data transfer. Till then the clock will be in low state. We can also call this as it as a clock stretching.
Okay. Okay.
We will discuss clock stretching.
Okay. Okay. Thanks, ma'am.
Okay, next, tell what is the case. You need to write the FSM.
Once it is go to the start state, we will be storing the data.
What is the start condition?
SDA is from high to low.
Once it is check in the ideal state, then only condition satisfy, it will go to the start state. Okay, next. Now it came to start, then register address. So what will happen in the register address?
We'll store into a temporary variable.
Temporary variable, which
Means we need to check whether whatever data address is sent, whether it is for reading and writing. For that particular scenario, we'll store the complete 8-bit.
Yeah, it will send 7-bit slave address plus read write bit.
okay, fine. So 8-bit address, that means total 8-bit address. In that 8-bit, 7-bit will be
For slave address.
1-bit will be
Read write.
okay. Next,
It will wait for the acknowledgement from the slave.
here in register address, this 8-bit address is getting from where?
From the master.
From the master. How the master is getting that data?
Bit by bit.
How the master is getting that data? That means here this Arduino is a microcontroller. It's a master. Okay. So how this board is getting that data?
There will
The
be from
code
a
will
processor.
Okay, you may think like here this board is directly dumped with the instructions. Arduino is directly dumped with the instructions. It will be generating those signals. But if we connect the same board to the processor, okay, so how the data is getting to this microcontroller? Nothing but here there will be one processor. The processor initiate the transfer. That data will be sending to this microcontroller, and that microcontroller is sending to the slave. So this is serial communication, but whatever the data is coming to the microcontroller, that will be parallel communication, right? So here whatever the 8-bit address is getting from the other master, before master, that data will be the parallel communication. We need to convert that parallel data to serial data here, correct?
Yes.
It is generated by master, but whatever the data is there, this master will convert the parallel data to serial data, okay, and send the serial data to the slave.
So, so when the master is converting the parallel data to serial data, the interaction is with the processor, right? Not with the slave.
Whenever master converting the parallel data to serial data, interaction
It
with the
interacts with
processor.
processor.
But master is not sending back data to the processor, right? It's sending forward to the slave.
So it's already converted. The serial data is already there in the master. That serial data will be sent, is it?
Yes, here master is converting in the sense we use the parallel to serial converter. That parallel to serial converter will convert the data to serial and send to the master input. Then that input data will be sent to the slave. Again, slave will receive that serial data. If slave want to send to some particular master again, suppose OLED display is there. OLED display, we get the output here, and that data will be connected to some other master also, right? That master may be any processor level. In SOC level, if you connect that may be parallel communication. So here the serial data again converted to the parallel data by using PISO or SIPO register. Okay, so we need to use both the cases. If there is requirement, we can put, or else just communicate between master to slave only, serial communication. Okay, so here serial to parallel. So again, slave will convert serial data to parallel and store the address. Till now it converted the address only. So it will store the address into the slave. So what is the acknowledgement signal? Which one it is generated by master or slave?
Slave.
So
Slave will generate the acknowledgement.
register acknowledgement is generated by slave. Okay. So what is meant by acknowledgement? Whatever the master sending to the slave, the particular address, if that address is available in the slave, it will send the acknowledgement signal as a 0. If not available, it will be sending acknowledgement signal as a 1. Right? So if address is available, slave will send acknowledgement signal as a 0, else slave will send acknowledgement as a 1, which we call as a not acknowledgement. Okay. So what we tell in the program, if acknowledgement signal is equal to 0, then write operation read operation is equal to 1 and read operation will be equal to write operation. So when will be it, when it is a write operation? Write read is equal to 0. Then write operation. Write the data or read the data to that particular acknowledgement. Okay. So now write. If it is a read operation, it directly jump to read data. If it is write operation, it directly jump to the write data state. So what we do in write operation?
We send the write data to the slave.
How much
8-bit
data?
data, 8-bit data to slave.
8-bit data sent to the slave, which is generated by master. Master will send the parallel to serial, and that serial data will be sent to the slave. Others, girls, are you able to understand? They will convert again serial data to parallel. Slave will store the data. Where it will store the data?
Slave memory.
Particular address.
Aditi, Akash, Akhil, Amartya, Ashwini, Riyan.
Yes.
Are you able to understand? Gopinath, Karthik, Manoj, Vita, Shubham, Roshini, and Muralidhar. Any doubts?
No.
Okay. So write data. This is present state. Okay. So what will be the next state?
It will
Slave will send an acknowledgement.
send an acknowledgement to the master that
Okay.
after reading the data.
Okay. If acknowledgement is 0, then what is the case? If acknowledgement is 1, then what is the case?
No, acknowledgement 1 means it will start reading the data, right? Yeah.
Okay. Acknowledgement 0 means, okay, first of all, acknowledgement will be generated by slave, same. Okay. So if acknowledgement is 0, slave received the data properly. Okay. If acknowledgement is 1, slave doesn't receive the data properly. That means,
Okay, 9th clock cycle, that thing.
suppose if acknowledgement signal is 0, then what is the case? Write
Data is
transfer is completed. Write data is successfully sent to the slave. So write
Yes.
transfer is completed. Then what is the next transfer? Write transfer is completed. Next, to which state it need to go?
And stop.
No, Mac is there, right?
Write is completed. Acknowledgement
Yeah.
is completed. We are in acknowledgement state now. So which
Mm.
state it will go once write is completed?
Start state.
Correct?
Start state.
Start state, okay. In which case, if acknowledgement is 0, okay. If acknowledgement is 1,
It has to wait for the correct data.
okay. Any other answers? Others? If acknowledgement is 0, write transfer will be completed. If you want to transfer another response, if you want to another transfer, that means another 8-bit of data, then what can we do? It will go to start state again. Okay. If you don't want another transfer, then just simply go to the read data. Next, if acknowledgement, that means not acknowledgement. If acknowledgement is 1, what happens? Go to stop state or start state simply. Go to stop or start state. Okay.
Okay.
Now
Hello.
read data. Yeah, tell.
No, from the master perspective, we are sending one address and data to particular slave. So if that address and things are this acknowledgement is the response provided by the slave, correct?
Yes.
So how I will know, means how the master will be getting that acknowledgement?
How the master is getting, in the sense, here we are writing, right? If acknowledgement is 0, acknowledgement is 1, which is connected to the master.
But this slave, in order to send a response and all, we require some address or things we required, correct?
Okay.
That point I'm not getting. If to receive those things, we have the slave address. Now, in order to communicate with the master, what slave will do?
Here, write data we are sending to the slave. If slave is receive the data properly, we need to write the condition for that, whether slave data is equal to the write data or not. If both are not equal, slave will send the signal ACK is equal to 0. This ACK 0 will be visible at output side for us. Okay, if it is a
Okay.
0 or internal signal, it will be connected with the signal, right? If it is a
Okay.
0, we will get the error response.
Okay.
If here, if it is 0, correct. 1 means error response.
Okay. It will be like an internal signal. Means.
Yes.
Okay. Thanks, ma'am.
Next, to read data. So what we
Um,
do in read? Yeah, tell.
Acknowledgement is 1 means either error is occurred,
Yes.
it will go to
Acknowledgement 0, 1 means error will be getting, or slave is in a busy state. If slave is in busy state also, it doesn't accept the current data. Okay, so then in that case also we will get a acknowledgement as a high. Whatever, it doesn't send the proper signal, whether it is due to busy state or whether it is due to incorrect output, like that we don't get. It just give the acknowledgement is high or low. That's it. That's what some of the limitations in I2C. But if you go to AHB or AXI protocol, even APB protocol, we have separate signals. If it is a busy, we will get the busy state. If it is a error, we will get the error state. But in I2C protocol, we have only acknowledgement signal. The slave can be any condition, whether it is busy due to previous transfer, or it may be got wrong value, whatever. The acknowledgement will show 1. Based on that, we need to correct the transfer again. We need to initiate the transfer again, or need to wait for the next transfer.
Okay, ma'am. Thank you.
Okay. Yeah.
Yes, ma'am.
Next, read data. What is mean by read data?
The master will read the data from the slave.
Read data is nothing but the data will be generated by the slave or master.
Slave.
Slave. 8-bit data generated by the slave. Okay. So this serial data, again, it will be converted to the parallel if it is sending some other master. If it is sending to same I2C master, no need to convert that parallel data. Okay. Suppose if slave is sending to some other master, it will convert serial to parallel data. Okay. Next.
Basically, slave won't convert, correct? Because if you want slave wants to send the data, it should be serial. It will reach that particular microcontroller in a serial. From a microcontroller, it
Connect
needs to
the
send
serial to parallel converters. That means slave will not directly convert. Will connect the between this slave to master. There will be converters, parallel to serial and serial to parallel. Those will be converted and sent to the serial data to the parallel data to the master. Again, parallel, that master will convert the parallel data to serial if it is transferring through I2C. If the data is transferring to APB, it will use same parallel data only. Did you understood?
No, if I have a sensor sending the data to I2C master means it is reading from the sensor, in the sense the only way of communication is serial, correct? Bit by bit, the sensor slave will be bit by bit, it will sending to that microcontroller. From the microcontroller, if it needs to send to the processor, there I will be using the serial to parallel communication converter, correct? So slave side, it will be always serial data, correct? In the master side, in the reading side only, at the boundary of the processor or microcontroller, there I will be using the serial to parallel converters, correct? In the slave side, there won't be any parallel on the response side or read side.
Side you are talking, that's okay, correct. You are telling within this slave to master only, within the circuit only. I am
Yes.
telling like, if it is a one IP, if you connect with another IP, then how the conversion will be happen? IP to IP, we need to convert through parallel only, right? Communicate through
Yes.
parallel only, right?
Yes.
IP.
Yes.
Suppose this
Yes.
is one IP. This some EPROM is connected to another IP. So here obviously we will have the parallel bus. These all are low speed peripherals. We connect to the APB protocol. So this slave data need to convert to the parallel data because we are using APB protocol. Through that APB, again you are connecting to some other I2C bus, I2C IP. Okay.
Okay.
Wait, let me explain. in a SOC, suppose this is one IP and I'm taking same IP only. These all are small peripheral IPs in SOC. Okay. And there are some high speed communication IPs also, like here we have a processor. Here we have a processor. Inside the processor subsystem, we will have a number of IPs which we call as a cores. And there is another IP called memory. Here we will have some memory slots or some DDR RAM or PI memory RAM ROM like that. There are some other IO peripherals are there. Okay, so these are different IP. Total 5 number of IPs are there. And this is IP, not a subsystem. Suppose it's a subsystem, inside it's a small block. IP is a small block. These all are n number of IPs. And here also it's a small block. Suppose if you think it is a small IP. Okay. Now the main communication between processor to here will be happen through bus. Processor
Yes.
side we use AXI bus, and here this side we use APB bus. So these all are serial communications only.
Okay.
Even this IP is connecting to multiple IPs here. Internal also we will have this parallel bus. Okay, through this parallel bus only all IPs are connecting like this. Okay, now
Okay.
this microcontroller within the IP, it's a serial communication. Now this EPROM is there. EPROM is a slave. From this master to EPROM, the data is communicating serially to here. If EPROM is connected to some other IP here, now this IP master from here to here through the bus, it will access parallel data only, right? Again, coming to within the IP, this microcontroller again send the data internal IP as a serial communication. But whatever the transfer is there IP to IP, it will access parallelly only. So now this serial, this slave need to convert the serial data to parallel, right?
Yes, yes, correct.
If I am drawing this block like this big, again here I have one microcontroller which is a master, another slave. So this is bus communicating as a bus. So whatever the serial data is there in EPROM, it will send the data as a parallel to this bus using APB protocol. Again here we are receiving the parallel data. Now this master need to convert this parallel data to serial, because here we are using I2C bus. This serial data is getting to the slave. Again the slave need to connect to the master. This master again here we will connect to the slave to serial to parallel, like that. It's communication between parallel to serial, serial to parallel, because everything is connected in a one chip, right? So this is how the communication will be happen.
Yeah, this is a same, right? All the Synopsys IPs will have this APB or AXI interfaces over them. Correct. That is the idea. Okay. Means any IP we purchase from Synopsys, whether it is a I2C or UART, everything will be covered over with a at the boundary level of the IP. It will be like a AXI or APB or HP interface, which will be interacting with the main interconnect AXI. Correct.
Okay. Just a second. Next. So read data acknowledgement. In read data, the data will be converted slave to serial to parallel, and master will convert again the parallel data to serial. Now read data acknowledgement. What will be happened in read data acknowledgement? If acknowledgement is 0, master received the data properly. If acknowledgement is 1, didn't receive properly. Right. So if acknowledgement is 0, then what will be the next state? If acknowledgement is 1, what is the next state? You need to understand that, right? Right. Try your own and stop wait. Stop wait in the sense directly don't go to stop state, right? So we need to wait until it go to stop state. So when it will go to stop state, whenever the transfer is completed, we need to wait until the transfer is completed. Then it will go to stop state. Okay. Next, again, start. Start is a default. So this is what the idea of finite state mission. Everyone try to write the draw the finite state mission. Tomorrow we'll see how to write the program. And there are two important concepts in I2C, which is a arbitration concept and clock stretching concept. We will discuss in the tomorrow session. Clock
Hello.
stretching and arbitration. Yeah, tell.
I have one. Basically, now if you have only have two lanes, and there is no signals to exactly check whether it is a protocol is a correct, because it is sending the data, only acknowledgement signal is coming. We are not checking any data is correct or not. So why we are still using this protocol? Because of only low power consideration.
Not only low power, first of all, within within chip communication, we have only I2C and SPI. So in SPI we use 4 lines. If you see MISO, MOSI signals, like that we use SPI. That is a more advanced, we get to know the error detection also. These are what simple I2C and SPI for normal devices. But if you go to system on chip design, we use PCIe, which is one of the most popular and also high speed. Compared to the PCIe, I2C will work at just 0.01% only. So PCIe is that what powerful, which can be replaced with I2C. But PCIe will work at a SOC with a very high speed communication only. Same as a I2C, but it have lot of features. No comparison with I2C actually. So that's what.
Okay.
Okay. Just work. I will share the PPT and I will show you FSM also. Just
Ma'am, please explain
overview.
me the
Try to write the. Tell.
ma'am, please summarize once the FSM part.
Okay. That's why you're opening the code. I will explain you through the code. Just try. Okay, see here. Whatever the signals reset, SCL, SDA, data out, data in, address out, we have considered all the signals here. Final state mission, whatever we draw here, what are the states or their ideal? Start, register address, nothing but first of all we are picking the address. If you compare this with the frame format here, same. First of all we took the ideal state. We are considering the statement here. SDA must be high to low, SCL must be constantly high. That's what the condition. Whenever the condition satisfies, it's a start condition. So we can initiate the transfer. We can transfer the address first. After sending 8-bit address, within the 8-bit only we have the read or write. Okay. it represents either write data or read data. If it is a 0, it jump to the write operation like this. If it is a 1, it will jump to the read operation. Okay, that depends on states. Next, acknowledgement. We need to check the acknowledgement signal and sending the data to the slave, acknowledgement, and finally stop condition. Conditions also we need to write in FSM. Okay, so I am showing you overall how to write the program for FSM. But first of all, try the final state mission diagram and then try to write the program. Okay, if you see here, the list of states. Ideal, starter, register address acknowledgement, write acknowledgement, read acknowledgement, stop wait state. Whatever the states are mentioned here, same. And next, these are for direction enable, readout, and address input. If you see here, what is the address in address out, comma, write or read concatenation operator. And next, preset for every FSM, it is a common logic and counter logic and write read logic common. See here, whenever start signal means SCL must be high and start enable must be high. Negate SDA, see properly, negate SDA. That means here it is a high to low. High to low is nothing but negative edge only, right? Stop condition low to high means positive edge. So whenever negate of SDA, SSEL must be constantly high. How we written the condition here? Always at the rate of negate SDA, SSEL is constantly high and start enable is also high. Then we can do the start condition. And coming to the stop, SDA must be pause edge. That means low to high. And SCL must be constantly high. That's what we call stop condition. Okay. Next, remaining states the same. Ideal state. So what is the next state? Start state. What is the next state? Register counter. What is the next state? So remaining all same. Just try whatever I explained till now. State right. We are counting 8 8-bit data and acknowledgement signal. Read 8-bit data. Read acknowledgement. Stop. Wait. Stop. And these all are enable signals. Tomorrow I will explain clearly. Okay, any other doubts? Shweta, Roshni, Manoj, Vinita.
No, it's okay.
No, ma'am.
No, ma'am.
Okay, practice well. Then only you can understand. Okay. We'll see.
Ma'am, I2c is verified by which language?
System Verilog only.
Okay.
System Verilog or UVM.
Okay.
Any circuit, any digital circuit, we verify using SV, UVM, OVM, VVM. All these methodologies we can use. Even we can verify using C language also, but finally that C language also converted into System Verilog. DPI interface will be there, right? A direct programming interface. So we can verify through C++. Some of the companies will verify through C++ only, but they will convert that code to the System Verilog using interface.
Okay. It is automatically converted or?
We need to write the program for that to convert.
Okay. It is more complicated.
But they have their own methodologies. Simple conversions will be there. Every company have their own formats.
Okay, ma'am. So we have to know C++ also.
No need. Just SV, UVM, enough. If you have more time, learn Python. Nowadays, Python is using for scripting.
Automation.
No need to learn Python.
Yes, ma'am.
Okay. Okay, then that's it. Thank you all.
Ma'am, scripting language we also have to know, like Perl.
Well,
For beginners also.
yes, better you can have some knowledge Anyway, if you enter into the industry, you can get to know at least just commands. If you know the commands, that would be okay.
Okay,
GVim
ma'am.
commands, the Linux commands, that enough.
BTech opening is after the pass out, no, ma'am. Before pass out in 8th semester, they won't offering
What?
placements to
Internships.
freshers. Internship they will give.
Internships only we can apply. But
Okay.
for in VLSI, we need to wait until passed out, completed. That means until June, July. Even software also same, but in campus placements we will get before. After June, July only you will get the offer letter, even in software.
Yes.
Same in VLSA also. But nowadays most of the product-based companies are hiring as a interns only, not directly.
On
Service-based
the
directly.
yes, ma'am. They check the performance, then they
Mm.
decide. Ma'am,
Okay. Yeah, tell.
ma'am, in today's market scenario, BTech they accept BTech student from tier 3 colleges like.
Yes, there are nowadays market is somewhat low. They are preferring mostly experienced engineers. But some companies, last we got drive from Advion Technologies and in semi technologies, some companies are hiring freshers also. Just yesterday only I sent resumes from our freshers. Just do practice and join for tomorrow session. Before that, everyone complete FSN, try to understand